Okay, it's my pleasure to introduce this week's speaker, Elia Fusi from University of Torino, who will speak to us today about special metrics and hypercomplex geometry. So please, Elia.
Yeah, thanks, Jeffrey, for the introduction, and thanks to the organizer for giving me the opportunity to give this talk. I'm really glad to be part of this series. And yeah, today I want to discuss a bit a joint work with Giovanni Gentili, which now is in Paris-Saclay, about special Hermitian special metric in hypercomplex geometry. So the plan for today's talk is in the first part, to discuss a bit preliminaries so that we can stay all on the same page. Then I'll move to discuss some motivation for our study and introduce maybe the main tool for us to get answer to some question we had. Then I'll move to discuss a bit about SLNH manifold and their interplay with the so-called quaternionic Gudosian metrics. Once we have this, I'll switch to another question we had, which is sort of the hypercomplex analog of an open question in complex geometry, which is nowadays known as the Fino-Vezzoni conjecture. And then finally, I'll conclude with with the introduction of the so-called HKT Einstein metrics, and I want to discuss a bit their property and analogies and differences from the Keller-Einstein case. So let me start just by define what's an hypercomplex structure again. So we fix our favorite 4n dimensional smooth manifold, and an hypercomplex structure will be just a pair of anti-commuting complex structure I and J. So once we have this, actually we have at our just in hand a whole two-sphere of complex structure, which is built out of I and J and their composition K. And I, J, and K, as we know, they satisfy the usual relation of quaternionic units. So from time to time, I will refer to the hypercomplex structure as H, as the whole two-sphere, or rather fixing a basis for H and of anti-commuting complex structure I and J. So examples of such manifolds are, of course, tori of 4n dimensions, but a more interesting example are the K3 surfaces, which are known to be hypercomplex and indeed hyperkähler. A non-Kähler examples can be produced, say, as follows. We take n copies of the quaternions, we delete the origin, and the standard hypercomplex structure is then invariant under the action of right multiplication by a given quaternion Q. Then what we can do is take the quotient. What we obtain is a smooth manifold which inherits from the universal cover the hypercomplex structure, an hypercomplex structure. And if we specialize in the case in which n is taken to be 1, what we obtain are the sum of the so-called quaternionic subsurfaces. Also, quaternionic subsurfaces can be obtained as a particular case of a more general class of examples, which are the so-called Joyce examples. which are nothing but product of compact Lie groups with a torus of suitable dimension. And what Joyce proved is that actually these manifolds always admit an hypercomplex structure, and indeed they admit plenty. And this such example will come back later in the talk. Okay, so once we have an hypercomplex structure, well, we obtain naturally a canonical connection, which is called the Obata connection, which is just defined as the unique torsion-free connection which preserves all the complex structure in H. And once we have this, we can say something about the holonomy, of course. So by this property, we know that the holonomy of the Obata connection will lie in the general linear group with quaternionic coefficients. But in this such group, we have, let's say, a preferred subgroup or a particular subgroup, which is the commutator subgroup. So if we ask the holonomy of the Obata connection to lie in the commutator subgroup, which is SLNH, then we will call the manifold an SLNH manifold. And the SLNH condition forces some strong restriction on the, let's say, complex geometry of the manifold. Indeed, if we have an SLNH manifold, then automatically all the canonical bundle we can construct out of the hypercomplex structure are holomorphically trivial. And it was a question by Verbitsky to prove the converse, but just for a given complex structure in H. So namely, if we have I, let's say, in H, such that the canonical bundle is holomorphically trivial, then the manifold has to be SLNH. Actually, this conjecture was disproved by Andrada and Torcahier, where they provided a compact example, which is a solved manifold, where the canonical bundle with respect to I is holomorphically trivial, but the one with respect to J is not. And so the manifold of course, cannot be SLNH. But actually, the converse is true whenever we add some metric condition on it. With metric condition, I mean the existence of some special hyperhermitian metric. And that was proved by Verbitsky for the first time, and then we will see our result. So let me switch to the metric side. So whenever we have a hypercomplex manifold, a Riemannian metric is called hyperhermitian if it's Hermitian with respect to any complex structure in H. Or equivalently, if it's Hermitian with respect to I, and the fundamental form associated to the metric is J anti-invariant. Now, in this setting, we have a special map, which is the following map psi, which acts on 1-1 form with respect to I, which are in J anti-invariant, and gives a 2-0 form with respect to I, in such a way that this correspondence is 1-1. And this map size is not only a bijection, but in some sense preserves some other property. Indeed, if we pick our 1-1 form to be real, what we obtain through the image of psi is a Q real form. namely the J of its conjugate is the form itself. And finally, if we impose or assume that gamma is positive in the sense of being the fundamental form of a Hermitian metric, what we obtain, an hyper-Hermitian metric, what we obtain is a Q-positive 2-0 form. Namely, this relation has to be satisfied for any x non-zero. But now, whenever we have an hyper-Hermitian metric, we have a preferred 1-1 form, which is real positive, and J anti-invariant, which is the fundamental form with respect to I. So we can apply this map, psi, and obtain a 2-0 form, this capital omega, which is known as a hyperkähler form of the metric G, which is Q real and Q positive, and we have also this relation on the volume forms. So as usual, I will confuse the 2-0 form associated to the hyper-Hermitian metric with the hyper-Hermitian metric itself. But as in complex geometry, let's say if we want to impose or define some special hyper-Hermitian metric, we will just require some cohomological condition on the 2-0 form, as we will see. Another feature that we have in this setting is this differential operator defined by Verbitsky, which is the del J, which is just defined taking the del bar operator with respect to I, and then twisting it with J, with the second complex structure. And as a first difference between the complex setting and the hypercomplex one, this differential operator will rise the holomorphic degree instead of the anti-holomorphic as del bar does. But nonetheless, it squares to 0 and anti-commutes with del. And so whenever we have this type of differential operator, we can cook up a cohomology ring, which is known as the quaternionic Bochern cohomology. It's just morally the same as the Bochern cohomology in complex geometry, and so it's the kernel of del intersected with the kernel of del J modulo the image of del J. And as we will see, this type of cohomology will come back often later. But as I was anticipating before, once we have an hyper-Hermitian metric, we can impose some cohomological conditions. And the very first type of cohomological condition that historically was defined is the, let's say, the notion of a special hyper-Hermitian metric was that of hyperkähler with torsion, which was introduced by Owen Papadopoulos and then studied by many authors, especially Grancharov and Poole. So we will say that an hyper-Hermitian metric is hyperkähler with torsion, or for short HKT, if the 2-0 form associated to that is del closed. That this definition is actually an equivalent condition given by Grancharov and Poon, but the original definition was that of was the following. So an HKT metric, a metric is HKT if all the bismuth connection we can build out of the hypercomplex hyper-Hermitian structure all coincides. And examples of these manifolds were found, and there are plenty. For instance, some of the Joyce examples are HKT, and that was proven by Offerman and Papadopoulos, and then by Grantcherov and Poon. But actually, the HKT metric is let me say that with their proof, not all the Joyce example are known to be HKT. Indeed, for an HKT metric to exist, some algebraic condition has to be satisfied. And so a first question that I will answer the last part of the talk is that are all the Joyce example HKT? But other example can be found in the realm of Neel manifolds, and actually all the Neel manifolds with abelian left invariant hypercomplex structure are HKT due to Dotti and Fino. But turning our attention into the SLNH condition, what Verbitsky proved is that if the converse of the question that I discussed before is true whenever the manifold admits an HKT metric. And so if we have an HKT metric and the canonical bundle with respect to I is holomorphically trivial, then automatically we have an SLNH manifold. But on the contrary, we have plenty of examples of SLNH manifold which do not admit HKT metrics. So the very first question that motivates our work is the following. Can we find metric and or homological condition which are equivalent to the SLNH1? And to do that, we needed to define these what we call the canonical forms, which are 2-1-0 forms with respect to I, alpha and beta, which are implicitly defined as follows. So these two forms have many properties which are quite relevant. First of all, let me focus on alpha. So the real part of alpha was already known, and indeed it coincides with the connection one form of the Basa connection on the canonical band. And just by its definition, alpha turns out to be del closed. But more importantly for us is that these alpha and beta characterize some or are encoding some information on both the torsion of the Chern connection or the bismuth connection, the Chern connection, and curvature information of both the Chern connection and the bismuth connection. So namely, we can recover the Lie form of the pair GI by just summing the real form of alpha and beta. And with this expression, we were able to prove that actually this form is independent of I. And so if we change complex structure in H, what we obtain computing the Lie form is just the same as the one with respect to I. And so by this, we get that also, of course, the real part of alpha is independent of I because it's the connection one form of the Basa connection. And so by this, we obtain also that the real part of beta is independent with respect to I. But more importantly, up to sign the action of I, the real part of alpha and the real part of beta are the primitive form of the first Chen-Ricci form and the first Bismuth-Ricci form. And so that's why they bring with them some important curvature information. So now alpha, we know that is del closed, so we can compute del J of alpha, which is a 2-0 form, and so it has to come through it has to be the image of a 1-1 form, which is J anti-invariant, and that 1-1 form is J anti-invariant part of the first Chen-Ricci form. And thanks to this expression, we can actually prove that the Chen scalar curvature of the hyperhermitian metric is independent with respect to I, so we can compute with respect to any complex structure in H, we obtain the same function, but it can be recovered as the trace up to a factor of del J alpha with respect to capital omega. Another feature we can deduce from the first expression in 4 is that actually, so now we have del J alpha is del J exact and del closed. And so it defines a cohomology class in the quaternionic Bochern cohomology, which turns out to be independent of the metric we choose. And so we call it the first quaternionic Bochern class. That class, we call it first quaternionic Bochern class of the hyper complex manifold.
I'm sorry.
Of course, this class will change if we change I
Elio?
and J.
Can you hear me?
Yeah, sorry.
Sorry, just so I'm sure, like in item 4, I mean, like this cohomology class just depends on the whole hypercomplex structure. It's not just I and J, right?
The cohomology class itself will change if we change if you change I and J. Yes, because the forms will change, but
even within the same hypercomplex triple class will change. I see. Okay.
But what I want to remark is that actually, the cohomology class will change, but the property of the cohomology of the first Bochern class to have a sign or vanish is independent of the choice. So if we assume that the first Bochern class, quaternionic Bochern class of I and J will vanish, then that of any pair of anti-commuting complex structure in H will vanish too. And the same if we impose it to have a sign, a positive representative or a negative representative. Yeah. And another property is that if we actually know that the first Bochern class of Mi is 0, then automatically the quaternionic Bochern class, the first quaternionic Bochern class will vanish too. And so in particular, if we have the canonical bundle holomorphically trivial, then what we obtain is that the quaternionic Bochern class will vanish. Okay, so once we have all these property in mind, let me focus on quaternionic Gudushian metrics. So quaternionic Gudushian metrics were introduced by Grancherov, Leishman, and Verbitsky as a tool to obtain somehow the Boukdar-Lamary type criterion for SL2H manifold. And they are defined as usual imposing a cohomological condition on the 2-0 form. So namely, we want the n-1 power of omega to be del J closed. And as the name suggests, actually, we can find a quaternionic Gauduchon metric in any conformal class on a compact SLNH manifold as an analog of the Gauduchon theorem in complex geometry. But outside the SLNH world, the existence of such metrics is not guaranteed. And indeed, the same counterexample that I cited before by Andrade and Tolkachier provides a compact manifold which do not admit any quaternionic Gauduchon metric. But nonetheless, having a quaternionic Gauduchon metric is precisely what we needed to obtain the equivalence between an equivalent condition to the SLNH1. So, and that's our first result. Let me, so we pick a compact hypercomplex manifold, then this manifold is SLNH if and only if the first quaternionic Bochern class is 0, and a quaternionic and M admits a quaternionic Gauduchon metric. And with this criterion, we can also state the following. So if we further assume the existence of a HKT metric, then the SLNH condition is equivalent to satisfy the del-del-bar lemma, to having the del-del-J lemma, which is an analog in this setting of the del-del-bar lemma. So now the question is, can we find some condition to have quaternionic Gauduchon metrics? And we try to address this problem firstly in the conformal class. So let me just restate the quaternionic Gauduchon condition as follows. So a quaternionic Gauduchon metric, an hyper-Hermitian metric will be quaternionic Gauduchon if the bismuth scalar curvature will satisfy this equation. So, namely, we want the bismuth scalar curvature to be minus twice the norm of beta. And this equation fits very nicely when we try to find quaternionic Gauduchon in the conformal class. So let me pick a quaternionic Gauduchon metric, and we can deform it conformally to a genuine Gauduchon metric, as in the complex sense, in the same conformal class. So this quaternionic Gauduchon metric will be hyper-Hermitian, and with this conformal change, we can deduce an equation for f, the logarithm of the conformal change, which has to satisfy the following. So if we want to find a quaternionic Gauduchon metric, we need to find a function which satisfies this. But out of this equation, we can deduce some necessary conditions. So first of all, integrating over the whole manifold, what we obtain is that the total bismuth scalar curvature of the Gauduchon metric has to be non-positive. And that's the bismuth Gauduchon degree of the conformal class. So that's the first necessary condition. Using the quaternionic Gauduchon condition as a cohomological condition, we can integrate this form which of course is 0, but integrating by parts, what we obtain is that this integral has to be 0. And this is actually equivalent or forces the following dichotomy, let's say. Either the difference between the Chen scalar curvature and twice the norm of alpha has to be 0 or has to change sign. And that's another necessary condition, which together with the previous one are also sufficient. So whenever we have a compact hyperhermitian metric and a Goudouchon metric, a Goudouchon metric satisfy the two necessary conditions, then we can find in the same conformal class a quaternionic Goudouchon metric, which is unique up to scaling as in the complex case. Let's say. Okay, but we are not so happy because the first one is not so easy to check if it's true or not, even the second one. And so we focus on finding some sufficient condition for the existence of quaternionic Goudouchon metrics without fixing any conformal class or without, let's say, in the global setting. And we were able to prove the following criterion using currents. So given a compact hypercomplex manifold, there will be no quaternionic Goudouchon metric if and only if we can build a non-zero Q positive del J exact to n current. Yeah. The strategy of this theorem is the usual one as in complex geometry, but out of this we can find a sufficient condition. So whenever we have a Q positive volume form, theta, which satisfies the following. So we require theta bar to be del J closed. Then we can actually find a quaternionic Goudouchon metric. As I was saying before, we know that on SLNH manifold we always have a quaternionic Goudouchon metric, and for instance, in that case, we have a Q positive volume form, which is also holomorphic, and so it naturally satisfies this. But out of that case, we actually don't know, and this condition is really pretty unexplored as now. So that's all for the SLNH case. Let me focus on the non-SLNH case. So the next question we want to address is, can we find some class of hyperhermitian metric which automatically force the first Bochern class, quaternionic Bochern class, to be, let's say, positive, semi-positive, but non-zero? And that's precisely the case for strong HKT metrics, which were introduced again by Owen Papadopoulos, and then the definition was reformulated by Verbitsky. So we will say that an HKT metric is strong if its conjugate is del J closed. And that's the reformulation of the original definition by Verbitsky. And the original definition was that the torsion of the Bismuth connection of the hyperhermitian structure is declosed. And this definition allows us to say that actually all the Hermitian pairs we can build out of the hypercomplex hyper-Hermitian structure are all SKT. And as a contrary of HKT matrix, examples of these metrics are quite rare. Some examples were provided by Grancherov and Poon, where they proved that a suitable extension of the opposite of the Cartan killing form on some Joyce example are is strong HKT. But this extension can be done just under the additional assumption of satisfying some algebraic condition, which is not always the case. So these metric are just on as a class of Joyce example. Other examples were constructed by Brienza, Finn, and Grancherov, where they show that the product of S3 and the mapping torus of an hyperkähler manifold constructed using an hyperkähler isometry is strong HKT. And we have plenty of information on strong HKT manifolds in quaternionic dimension 2, due to, again, Brienza, Fino, Grancherov, and Verbitsky, where they show that any compact dimensional, simply connected non-hyperkähler strong HKT manifold has the structure of a Hopf fibration over a 4-dimensional orbifold. And very recently, Papadopoulos, under the additional assumption that the fibration is a principal bundle, gave the full classification. So the manifold is either diffeomorphic to SU3 or isomorphic to R times S3 times B, where B is one of the following three manifold, where K3 is a K3 surface. Okay, so in these regards, what we were concerned about was the coexistence of strong HKT metric with other type of hyper-Hermitian metrics. And so in this case, I want to recall an open conjecture by Fino and Vezzoni in complex geometry, which asserts that on a complex manifold, SKT and balanced metric can coexist only on Kähler manifolds. And this question is still open in the full generality, but we have plenty of evidences for its validity. Here I cited some. So a natural question is in this setting is the following. So can we find a non-hyperkähler compact manifold which admits both a strong HKT metric and an hyper-Hermitian balanced metric? Let me say that the only instance where this was proved to be impossible is due to Verbitsky, which proves that in at least 3 quaternionic dimensions, both a strong HKT metric and a balanced HKT metric cannot coexist in the same quaternionic Bot-Chain class. So let me emphasize that the balanced metric is required to be HKT2, and that's forcing some important information on the manifold itself. Indeed, such metrics are automatically Cherenkov flat, and that's forcing, for instance, the first Bot-Chain class, the quaternionic one, to be 0. So we try to address this question in the full generality, and our main tool is the following lemma. It's quite easy to prove, but it's really important for us. So we fix strong HKT metric in dimension at least 2, and then we can actually give explicit expression of the del J of alpha. And out of this, we can say something more. So in particular, of course, this 2-0 form will be positive semi-definite, and it will be 0 if and only if the metric is hyperkähler. Moreover, if the metric is supposed to be not hyperkähler and the manifold is compact, automatically what we obtain is that the first Bochern class is non-zero, and in particular is Q semi-positive, has a representative which is Q semi-positive. And out of this, we, using the criterion on SLNH, on the SLNH condition as before, we obtain that actually a strong HKT manifold cannot be SLNH. But say this lemma allow us to answer the question that I posed before, saying that on a compact strong HKT manifold, which is not hyperkähler, there cannot be any balanced hyperemission metric. So let me want to discuss a bit the proof, because it's quite easy actually once we have all these ingredients. So by the assumption and the lemma before, we know that the del J of alpha of the strong HKT metric is Q semi-positive, definite, and non-zero, because it's not hyperkähler. So assuming the existence of a balanced hyperemission metric, what we can say is that the total scalar curvature of such metric is 0. So using again the balanced condition, we can solve the Poisson equation and can write this scalar curvature of the balanced metric as the Laplacian of some function. And now we know that del J of alpha of omega and that of omega tilde will represent the same, will lie in the same cohomology class. And so the difference will be del J exact by a function psi. So we can trace this equation with respect to the balanced metric. And on the left-hand side, what we obtain is a positive function, non-negative function. And on the right-hand side, we have a Laplacian. So we can actually apply the maximum principle to say that everything has to be 0. So in particular, the trace has to be 0, but now using again the Q semi-positivity, this is possible if and only if the J of alpha is 0. And that's a contradiction. Right. Now, by the lemma above, we know that actually a strong HKT metric cannot have its del J alpha equal to 0 out of the hyperkähler setting. So the next question is what type of curvature condition can a strong HKT metric satisfy? And to answer partially this question, we introduced the following hyperemission metrics, which we call the Einstein, and they are defined by requiring the following Einstein type equation, where we ask for the del J of alpha to be a multiple of the metric itself. If we further know that the metric is HKT, we will call the metric HKT Einstein. Of course, easy remark is that whenever we know that lambda is non-zero, then automatically the metric has to be HKT. But in the case in which lambda is non-zero, of course, this is not guaranteed. And example of this type of metrics are, of course, hyperkähler metrics, which are Einstein and with lambda equal to 0, because they are Ricci flat. Other example can be found in dimension 1. Indeed, any quaternionic curve admits a HKT Einstein metric. Actually, up to conformal equivalence, quaternionic curves are just 3, which are four-dimensional torus, K3 surfaces, which are hyperkähler. The third example are quaternionic subsurfaces, which provide an example of non-hyperkähler HKT Einstein metric, which is in particular strong HKT. And then what we were able to prove is that any of the Joyce example admit HKT Einstein metric with a positive, with the lambda, say, equal to 1. And that's, let's say, answering the question, the first question that I posed at the very start. Because in particular, this type of metric provides HKT metrics on any Joyce example, which are further Einstein in this sense. As for non-HKT example, we know that any left invariant hyperemission metric on an hypercomplex manifold is Ricci flat, and so in particular is Einstein with 0 Einstein factor. And some of them, of course, are not HKT. So, but in some sense, this definition and the study of HKT Einstein is quite similar in some sense to the study of Kähler-Einstein metrics. But what we found, which was quite surprising for us, is that in this case we don't have the general type case if we want to compare with Kähler-Einstein metrics. So, namely, whenever we have a HKT Einstein manifold on a compact manifold, the scalar curvature has to be non-negative, and so the Einstein factor has to be non-negative, with equality precisely when the manifold is SLNH. And so, so we require, we found another, if you want, equivalent condition for the SLNH. And I just want to remark that the compactness is really necessary here, because we managed to find examples of HKT Einstein metrics with a negative scalar curvature, but on solvable groups which are not unimodular. And so in particular, we cannot, let's say, quotient out to obtain something compact, because the non-unimodularity prevents this in some sense. And just to conclude, want to give some naive question, really naive. Let's say in analogy with the Kähler-Einstein case. So let me just start with a compact complex manifold with a positive first quaternionic Bochern class. And the question is whether we can find a unique up to the action of some group HKT-Einstein metric in this cohomology class. And this is, of course, equivalent to, solving the following quaternionic Monge-Ampère. But this is really a naive question. We don't know whether this can be found in general, and what group, what uniqueness result we can expect, and nothing certain, let's say. Yeah, I think it's all. Thanks for the attention.
Thanks, Elia. Are there questions? Okay, well, if not, let's thank Ali again for the very nice talk. Or, oh, maybe there is.
Sorry.
Okay. Hi, Elia. Thanks for the
Hi.
nice talk.
Yeah,
I am Laura. I am with Alejandro, but I am Laura Barberis. I have a question concerning the following. In fact, do you think that it has been studied when for hyper-Hermitian manifold, what happens when the three Chern connections coincide? So it's in HKT case, you have that the bismuth connections are all the same.
Yes.
So what do you know? What can happen for the Chern connections?
I guess pretty sure that they have to be hyperkähler. So the coincidence of the Chern connection forces the hyperkähler condition. But I think it's something that is not in the literature. It's really easy. Some really easy argument, but I didn't find it in the literature explicitly stated, let's say.
Okay.
Okay.
Okay. Thank you.
So any other questions or comments, remarks? So if it is not the case, thanks Elia again for the nice talk. And thank you for joining this meeting. Okay, so see you next week. Bye.